Hello, dear students. Welcome to the channel and welcome back again to this playlist in which we are discussing about the transmission line modeling and performance. And just a quick recap what we have done until now. We have initially seen what is a transmission line. We have seen basics. We have seen what are the types of transmission line. We have seen short transmission line in detail. We have seen medium transmission line had two different analogies to represent a medium transmission line. One is called nominal pi and other one is called nominal t. So we saw them in detail. We derived the ABCD constants parameters or the generalized constant parameters for both nominal t and nominal pi terminologies. After that, what did we do? We saw the long transmission line. What is a long transmission line? And we did the analysis of the long transmission line with the method which is named as rigorous method. So today what we are going to do again, following the same formula which we were doing, we are going to derive the generalized parameters or ABCD parameters for long transmission lines today. We are also going to do a little bit analysis. We are going to see and we are going to interpret some of the equations which we will derive, and later on I will discuss about Ferranti effect, which many of you might already know. So and this lecture, this particular lecture which I'm going to talk about today, it is heavily based on the previous lecture. So uh, today the derivation of ABCD parameters of this um, long transmission lines, to understand that you must know the rigorous method. You must have idea what is the rigorous method and how does it works and what operations we end up with, the operations and final formulas for sending in voltage and sending in current, and based on that we are going to derive the ABCD parameters only. So you must have some idea what is the long transmission line and what is the rigorous method. So if you have no idea about rigorous method, no need to worry. We have explained it everything in detail in the previous lecture. So uh, you can just click on the I button which will be flashing on the top right hand side corner of your screen, and follow that lecture, and then again come back to this lecture and see it. The second thing which I must mention, that to understand this lecture you must have some idea about the general principles of power system. So if you don't have any idea about the power system, you might not find this lecture series very entertaining or very much informative. So we have solution for that as well. We have created a whole video series which discusses the general principles of power systems. So you can just go on that playlist and you can watch it, and then you can learn the basics of power system. So the link for that playlist has been provided in the description below. So if you want to know more about it, if you are into power system stuff, if you want to know the gender, if you want to revise or if you want to know from the basics about the power system, just click on that and uh, you can follow along. Now as you are already as you're already here, let's start discussing about the derivation of ABCD parameters based on the rigorous method. So last time when we discussed the rigorous method, what did we do? We came up with the formulas for sending in voltage and sending in current in the form of Vs and Is, and it had some the values it consisted were the values of receiving end current and receiving end voltage, and except for that y and z. And what was the y and z here? The y and z was the total series impedance and my total shunt admittance. Okay, so uh, let me quickly take you to the um, image representation of that so you will understand it better. Okay, so what was Y and Z? It was total series impedance and total shunt admittance. As you can see here, collectively, I'm not talking about individual or per unit. I'm talking about collectively because I'm talking about capital Z and capital Y here. So we have derived that, and now based on that, we want to find out the generalized constants or the ABCD parameters for my long transmission line. Okay, so firstly, let's take the formulas for Vs and Is, the sending end voltage and sending end current, and we are taking it from the rigorous method. And now what we will do, we will simply compare these equations with my formula for generalized constants. Remember what was the formula for generalized constants? Let me show it to you here. See, see the image on the right hand side. Here we are having the formula for generalized constant. Vs is equals to A into Vr plus B into Ir, and Is is equals to C into Vr plus D into Ir. So now compare these two equations with the equations which we just came up across with. Where did it go? Here. Okay, so Vs is equals to Vr cos h y under root y z plus Ir under root z by y sin h under root yz plus Is is equals to, sorry, not plus, the other formula, Is is equals to Vr under root y by z sin h under root yz plus Ir cos h under root yz. When you compare it, you will find the value of A will have great significance with this cos h under root az, because except for A, other term was there was only Vr, right? See here, come here and see again. Where did it go? Here, see, except for Vr we have A, and except for Ir we are having B, right? So when we compare this formula, when we compare both of these formulas, we will find the values of A, B, C, and D. So A and D again, remember, if you remember, we discussed about the verification process of my generalized constants. So in order to verify it, I've told you that the values of A and D will always remain equal. Both the values of A and D will always be same. So here values of A and D are coming same again, cos h under root yz, and uh, from this formula we can see what will be the value of B. It will be under root of z by y sin h under root yz, because except for Ir the term is B, so this term is B. And same ways, except for Vr, in this second formula, in the formula of Is, except for Vr, the other remaining term is C. So what is the other remaining term? It is under root of z, under root of y by z sin h under root of yz. And one more time, if you want to verify it, you what you can do, you can take the multiplication, you can take this formula AD minus BC, and you can do the math, do multiplication, do the subtraction, and at the end of this whole arithmetic operation, what you will be left with will be only 1. If your answer is 1, that means the parameters which you have derived based on this rigorous method are correct. If your answer is not 1, if it is anything except for 1, that means you again have to do the work, do the math, and you have to derive this generalized constants for long transmission lines. Okay, and it is pretty much same for all the type of lines, for medium, nominal, pi, nominal t, and everything, right? So that was the determination of generalized constant for long transmission line. Now let's come to the other discussion part, the interpretation of the equation part. So firstly, let's see about a term which is called gamma. So what is a gamma? Actually, gamma is nothing but square root of the product of my total series impedance. I'm taking my total series impedance and I am doing its product. I'm multiplying it with what? I'm multiplying it with the shunt admittance per unit length. Okay, I'm taking total series impedance, then I'm taking shunt admittance per unit length. I'm doing the product of it and I'm taking square root of it, and the answer which I will be having, I will call that answer gamma. Okay, and we call this gamma term propagation constant, and it is always can be represented in the form of complex number, as alpha plus j beta. And what will be this alpha and beta? So alpha will be the real part, and beta will be imaginary part. As you can see, j is with beta. What will you call alpha and beta? We will call alpha as attenuation constant, and we will call beta as phase constant. And now the equations which we derived earlier uh, can be again represented in the earlier, I mean, in previous lecture, of course. So it can again be represented with these formulas, right? Because we are representing it in the manner of complex numbers, so we can represent it this way: vr plus ir into zc divided by 2 into e raised to alpha x into e raised to j beta, that become your complex part, plus vr minus ir into zc divided by 2 e raised to minus alpha x into e raised to minus j beta x. Same ways we can write the formula for ix. It will be vr divided by zc plus ir divided by 2 into e raised to alpha x into e raised to j beta x minus vr divided by zc again minus ir this time divided by 2 into e raised to minus alpha x into e raised to minus j beta x, right? So and this which we have written will be for the whole length of your long transmission line. Okay, this vx and ix will be the voltage and current for the whole transmission line. But if I want to find the instantaneous voltage vx of t, how can I find it? So I can only take the real part of this whole expression. So it can be represented as a real part of root 2, then plus same expression vr plus ir divided by zc vr plus ir zc divided by 2 into e raised to alpha x into e raised to j omega t plus beta x. This time we added omega t with beta, then again plus root 2 vr minus ir zc divided by 2, and this time again we will take e raised to minus alpha x into e raised to j omega t minus beta x, right? Simple, we are just taking the real part. Now the instantaneous voltage, this the formula of which we have just derived, will have two terms, right? Which will be a function of two variables, right? What are these variables? The variables will be time and distance, and hence this instantaneous voltage, which is a function of time and distance, will represent two traveling waves. Okay, so let's come to that two traveling waves. First, let's discuss about incident wave. So the first term, which was e raised to alpha x, it changes the magnitude, and it changes the magnitude with x. Okay, and the term e raised to j beta x will cause the shift in the phase beta, and it will shift in the phase beta per unit change in your length. Okay, so in image you can see we are having it. Let me tell you a little bit more in detail, it will get clear more. So now you know the as we are having the distance, let's call the distance x as we are taking here. So the distance x from the receiving end will increase the first term in the equation. What was the first term in the equation? It was the root 2 vr plus ir zc divided by 2 and e raised to alpha x dot e raised to j omega t plus beta x. This term will also increase in amplitude. Okay, it will not normally increase, it will increase exponentially. It will increase exponentially, and it will advances in phase. What it will do? It will advances in phase, and as it is advancing in phase, so after some time, let's call this time delta t, the distribution distribution which is advancing in the distance will be by the phase will be omega delta t divided by beta. So here you can see the distribution was advancing in phase, and how much did it advance? It is advances omega delta t divided by beta, right? Now this wave which is traveling towards the receiving end, we call this wave incident wave. Okay, it is traveling towards my what do you call it, receiving end, right? And see what is happening here. The amplitude of this wave is decreasing exponentially while going from sending end to receiving end, as you can see here, right? Its amplitude is decreasing. Now let's try to focus on the other term which we saw, in which we are taking subtraction. So the other term was, come here and see what was the other term here. Vr divide sorry, here root 2 Vr minus IR ZC divided by 2 e raised to minus alpha x into j e raised to j omega t minus beta x. Okay, so what will happen about it? It will decrease. It will decrease in magnitude exponentially this time again. As you can see, there is a negative sign with alpha here. It was we had positive sign with alpha when it was increasing. Now we have negative sign with alpha. Then what will happen? It will decrease in magnitude, right, exponentially, and it will retarded in the phase from receiving end towards the sending end, right? And this wave, we will call this wave a reflected wave. What will we call this wave? We will call this wave a reflected wave. And the equation which we saw, the equation of instantaneous current, uh, this equation will be similar to the voltage. And as we are having the equation for instantaneous current which is similar to voltage equation, as you can see this equation here, because based on this equation we got this equation. So based on this current equation you can also get the similar equation, right? So the equation for the instantaneous current will be similar to the voltage equation. And based on that we can consider that uh, it may be considered to be composed of incident and reflected currents, right? Because this was instantaneous voltage, so current will also be instantaneous, right? So incident current or reflected current. And at any point along the line, what will be the value of voltage? Come here and say, tell me, at any point along the line what will be the value of my voltage, right? At any point along the line the voltage will be the sum of incident and reflected voltage waves, right? This is my incident wave, this is my reflected wave, right? So the sum of both of these will be the value of your voltage. And same thing we can say about the current as well, right? About the current wave as well. At the end of the day we are having almost identical formulas, almost similar formulas we are having. We are just having this negative sign between them. So that's what a thing which is distinguishing. And we are just taking ZC in denominator when we are talking about current, and we took ZC in multiplication with IR when we were talking about voltage. So that we can do if the load impedance, my load impedance, what was my load impedance? It was ZL. So if ZL will be equal to the ZC, then what will happen? The line will be terminated in its characteristic impedance, and then reflected voltage wave will be 0, right? Because what will happen? VR minus ZC, VR minus ZC into IR will be 0, right? And such kind of lines which are terminated in its characteristic impedance are called infinite lines. Okay, these lines which are terminated in its characteristic impedance will be called infinite lines. And in such conditions of infinite lines, what happens? uh, the incident wave will cannot be distinguished between the will not be able to distinguish between termination and continuation of your line, right? It will not be able to take decision if shall it continue to move on, or shall it terminate. Like, it will not be able to distinguish between the termination of line and the continuation of line. And when such phenomena occurs, when such thing occurs, what do? We call that phenomena in power system. We call that phenomena surge impedance, and we can denote this surge impedance with the symbol ZC. Right? We denote the surge impedance with the symbol ZC. So that was your surge impedance, and that was your long transmission line interpretation of equations. Now let's move towards the other definition which I wanted to not definition but about one of the effects which I wanted to discuss. In power system, there are 3 to 4 effects which are always considered while doing any calculations or while doing um, any while doing any planning, right? So what are those 4 effects? So first effect is called skin effect. The second one is called proximity effect. The third one is called Ferranti effect, and fourth one is called corona effect. Okay, in previous or 2 or 3 lectures ago, we have discussed about the corona effect in very like very small detail, very small glimpse I've given. But today we are going to discuss about the Ferranti effect first. There are skin effect and proximity effects as well. So let me quickly tell you what is a skin effect. That what happens the when we have alternating current flow, or let's say the tendency of my AC current flow will be always towards the concentrate will always be concentrating towards the outer surface of my conductor, right? As if the no current is flowing in the central portion of the conductor. So the current density, I'm talking about the conductor, huh? I'm talking about inside of conductor. So the current density on the outer portion of my conductor will be higher, and the current density in the center of my conductor will be close to nil or almost zero. And uh, that is for AC current only. Okay, I'm talking about AC current only. And when such thing happens, we call it skin effect. With DC current, no such thing happens, because what happens in DC current, the current will be uniformly distributed and it flows through the whole cross section of your cable, or cross section of your conductor. So there is no skin effect in DC, but yeah, there is a skin effect in AC, right? And there are different remedies to overcome this skin effect. We use a conductor called ACSR, and a lot of things, aluminum coated steel reinforced conductors we use. So there are so many remedies. We can get rid of it by placing a central conductor as a steel conductor, and the other conductors around it, which will be coated in aluminum. No, sorry, central conductor will be aluminum core, and the other conductors will be in the steel. We can even do the alternate, right? We can even take steel in the center as well, and we can strand it with aluminum, right, in a twisted shape. So we can do that too. Now quickly coming to the proximity effect. So what happens in proximity effect, that my flux flux of 2 conductors, let's say I'm having 2 conductors A and B. So when the first conductor, A conductor, will carry my AC current, the flux of that conductor will link with the other conductor B, and the half of the portion of the B conductor which is facing the A conductor will what will happen, will have more flux linking than the other portion, right? And this effect is called proximity effect. Now coming to the third effect, the Ferranti effect. Okay, so what is Ferranti effect? That in power system, Ferranti effect is mostly used in the power system terminologies. So what happens in Ferranti effect that uh, uh, when sending in voltage, let's say I'm having a system, so I have sending in voltage and I have receiving in voltage, right? So in general conditions, what happens when we supply a voltage and receiving end voltage, there is some load connected and it is consuming your power, right? So sending in normal conditions, sending in voltage is always greater than the receiving end voltage, because there will be some losses in between, right? There will be line loss, copper loss, and all other losses, right? But uh, in such phenomena, what happens, the receiving end voltage increases. If the receiving end voltage increases such that it surpasses my sending in voltage, that when receiving end voltage surpasses the sending end voltage, or receiving end voltage is greater than the sending end voltage, such phenomena is called Ferranti effect. And why does it happen? It happens because of the high capacitance of transmission line, which is circulating the capacitance openly, or my system, which was um, previously operating on very high load and now it is operating on very light load. So in such cases, what happens, my uh, receiving end voltage will uh, surpass my sending in voltage, and this effect is called Ferranti effect. It was named after a scientist known as Z Ferranti. And uh, what except for that, what do we do? Let's discuss it in bit detail. So as you can see here, I'm having sending in voltage, receiving in voltage, and ZL, which is open. So the line which is being charged, and line current of IC which is flowing through my line, which is led by this VR, as you can see, what will happen, it will lead by 90-degree, assuming capacitance of line. See this phasor diagram. I'm taking VR as my reference vector, and then my, because as IC is having capacitance value, then it will lead my current by 90-degree, right? So capacitance of the line is not distributed, but as if it is concentrated to the receiving end. We will take it like that. Then the resistance drop, IC into R, which will be in the phase with IC, and voltage ICXC by 90-degree will lead my VR as well, right? So as you can see, we are taking VR here on as a reference, and then we are taking IC, which is leading my VR by 90-degree. And see, uh, if you try to draw it this VS, the length of VS vector is shorter than the length of VR vector, right? Which means the amplitude of VS vector is less than amplitude of VR vector. Again, this ICR, it will be in phase with my current, so you can see it in phase with your current. And this ICXC, it will be 90-degree shifted because of capacitance effect, right? Then your current, so it will be here. And as you can see, VS is less than VR here, because receiving end voltage is greater than sending end voltage, right? So that is your Ferranti effect. This uh, capacitance current IC will produce loss of power, which means there will be copper loss in your line, and this copper loss in the line is given as IC square R divided by 3 for one phase. For multiple phases, you can give it by uh, for multiple phases, you can give it by IC square by R for 3 phases, right? So that was the Ferranti effect. And in the we will keep this lecture till here, and in the next lecture we will discuss further topics. We have to discuss about the tuned power lines, and we have to discuss about the circle diagram as well. So I will end this lecture here. If you have any doubts, any queries, or if there is anything you want to share with me, if there is some feedback you want to give regarding the videos, or if you want to ask something, feel free to mention your doubts and feedback in the comment section below. I will try to answer them as quick as possible, and I will try to answer as many as possible. So I will be seeing you in the next lecture, and till then, take care of yourself, and goodbye everyone. Thank you very much for listening.